Okay. Finally, for today, let's study a couple of properties about preservation of measurability. The first one is rather simple, so it is here, the proposition 3.8. What does it say? It says that measurability is preserved if you do compositions. And how does it look when you draw it? It looks like this, that there's some space S, there's another space S prime, and a third space S prime prime. We assume that F is a map from there to there, and then we have another map G, which is further mapping things towards S prime prime. Then the composition map is the map that you get when you first map with F and then with G. And this operation, first with F and then with G, is denoted by G circle F. Why F is first, then G? It looks a little bit wrong order, but if you think, okay, if I map a member of S, so how would I do this function G circle F? I would do it G F of S. And this is the reason why G is in front and F is next. That's the reason that it looks visually clearer, maybe this way. And this proposition claims that if F is measurable, so we have some measurable structure, calligraphic as there, we have some calligraphic there, and if G is measurable and we have a third measurable sigma algebra there, so we have sigma algebra, sigma algebra, sigma algebra there. So if F and G are measurable, then so is the composition. That's the message of the theorem here. The proof is very simple. I think I could convince you by words. Take any measurable set here and look at the pre-image of what this composite function does. So we first we map the set. Let's say we have a set, let's call it A prime prime here. We take the pre-image, so actually we take first the pre-image by G and then the pre-image by F. This is the way to get the pre-image of the composite function. So which points eventually map into A prime prime are those where first G needs to map them into there and then F needs to map into there. So it's a simple, very simple proof which you can read in the lecture notes, and that's where the small proof is. Now that you have seen the picture, it should be very easy read. Are there questions about compositions of measurable functions? Maybe a tiny remark. The same composition theorem works in topology. So if you have a F is continuous, G is continuous, then so is the composition of continuous functions. That is as well continuous. Measurability and continuity work in the same manner in this sense. Then this is the results that we looked at already. How to verify measurability, the abstract theorem about this good sigma algebra. And we looked at these corollaries. But the remaining topic that we have still a couple of minutes is to look at if we take two measurable functions and now we take measurable functions with values on the real line. So for such functions, we can define the sum of the functions, and it's again a new function. The sum function is defined in the obvious way, so the value of the sum function is the sum of the values of the functions. Okay. This is called the pointwise sum. The pointwise product is similarly defined, so it's a function denoted this way. The value of the pointwise product at point S is the product of the values of the functions. And finally, there's the pointwise scalar multiplication. Take a scalar and a function, so then the pointwise scalar product is defined as using this formula that you see over there. So starting with functions, we can define sum, product and scalar multiples, basic algebra for functions with real values. What happens to measurability if I take two measurable function f1 and a measurable function f2? What happens is that the sum of these is also a measurable function. Why is that true? It is true because there's a proof here. And the proof says if you start with something measurable, by the way, this M here denotes the measurable real functions on the space S. It's a shorthand for that. So this theorem or proposition tells us that measurability of functions is preserved in scalar multiplication, in sums, and in pointwise products. The result looks simple. Actually, I should tell you that this proof is not very simple. So the proof for the property 2, it looks quite innocent, and it looks like, okay, this should be very trivial to prove. Like, imagine how easy linear algebra is. So take some functions and you sum them coordinate-wise. So should be trivial to do. Actually, if you look at this proof, it's not trivial at all, in my opinion. Why? Because it requires working with rational numbers and knowing that the rational numbers form a countable set. And it requires you to represent, in this proof, this set of values for which the sum is bigger than some threshold C as a countable union of something else. So actually, this proof is complicated. I recommend you to try to have a look at this proof and tell me if you find it simple. If yes, be happy. If you found it complicated, maybe if you can send me a message in Julep or email. So if needed, we could look at it in more detail if you like. Okay. Otherwise, we don't speak about this more today, but if needed, we speak about it later. Finally, in addition to basic algebra or real functions, we can also do analytical things for real functions, namely, assume that we have a sequence of functions with values in the real line. We can define the supremum of these functions and infimum of these functions pointwise using the obvious ways. So the pointwise supremum is the supremum of the values of the functions. The pointwise infimum at point S is the infimum of the values of the function at the point. Also, because we want to be flexible, it's 12 o'clock. Please bear maybe 2 more minutes so we can finish. So we can also extend these functions to have values on the extended real line. And now this means also including minus infinity. And we can do it by adding two values, plus and minus infinity, using the kind of obvious rules. If you know how to add the plus infinity, as we discussed previously, you know how to extend the definition to minus infinity as well. It's the same thing there. So we can look at supremum and infimum on the extended real line and think about these as functions as well. Okay, we need to think, okay, what are measurable sets on the extended real line? So these are, one way to define these is to kind of use a map which maps the topology of a compact interval into this, and that's one way to do it. And then you define this Borel sigma algebra using the topology on the extended real line. We might come back to this later if we really need it. For now, we might actually maybe just conclude that, okay, one more thing, pointwise lim sup and lim inf. This is also something that you can define. But finally, the main theorem here is that if you do pointwise supremum, infimum, lim sup, lim inf of functions which are measurable, then the outcome is going to be measurable as well. This proof is not so difficult, actually. I think it's easier than the to prove that the sum of two functions is measurable. In my opinion, this is quite an easy proof. It's maybe a matter of just understanding what a supremum means. So when you understand what this means, you can do this, or you can read this proof. Nothing special about this basic analysis. As a corollary, if you know that lim sup and lim inf are measurable, then in case we are looking at the sequence of functions which do have a limit. So then this limit is a measurable function as well. So the limit of a measurable function is a measurable function. And as we say, this is something that we will skip for today, and we will come back to this maybe after 2 weeks or 1 week. Okay, that's the conclusion. It's been a kind of very, let's say, I would call this a very dry day of lectures, because to prove that a function is measurable or understand, in some sense, it's a boring thing, because as we learned, you start with measurable, you take a sum, you do it, whatever you do, or you take the limit or supremum, you always remain in the measurable domain. So actually, it's not as easy at all to construct a non-measurable function. Or let's say it's equally hard than to construct a non-measurable Borel set.